Thanks for joining. Hopefully, everyone had a really good holidays. Yeah. So last time, I'll start out with like a kind of recap of where we ended up last time. So last time we essentially discussed how do we want to model manifest DVs and in terms of change detection, and like should manifest DVs be a separate entry or not. And there was general consensus from the last discussion that manifest DVs should probably be in line with the manifest entry itself, and the diff DV would also be and we would track changes to manifest DVs through a diff DV. So that was kind of the general consensus. What I did. Oh, sorry. Go ahead.
I have one thing to add after you're done.
Oh, okay, sure. Yeah. So that's basically where we ended up. Combined entry, not necessarily in line. How are you drawing the distinction?
So I think, and this might be what Anoop was going to say, I thought that where we had gotten to was like, rather than having an entry for a manifest DV and an entry for a manifest file that have to be, reconciled and found, we said that's going to be one entry, and you'll have the DV information, whatever that is, in the same place as the manifest information.
Correct.
But I don't think that we have made a decision on whether the entire DV content can be within the root metadata file, or whether we want to support like a Puffin DV like we use for for data files. Is that correct?
That's an accurate summary. Yeah, I think that's actually, going to lead into our conversation today. But yeah, so basically, yeah, to just reiterate, the conclusion from last time is really about the combined entry, but the contents of the DV, yeah, I think it's still something we should work through, if it should be necessarily in line, or if there's an argument to be made that it's that there are use cases for having an out of line manifest DV. Let's see. I think after that discussion, just like yesterday, Anoop, thank you for updating the proposal with the updated entry structure. So that's really helpful. I think folks can go take a look. Let's see. I also updated. I took the change detection section that Stephen had worked on, the pseudocode. I did like a little bit more of a basically a I would say more, I guess, like, not, I wouldn't say engine related, but like more I guess detailed level of pseudocode, I guess, for figuring out like, are there cases where things like row lineage stats would be beneficial in change detections. So basically representing the computations as like scans and joins, and seeing like where we're exactly passing in filters in the row change detection, to see if there's any cases where like we might need to like enhance the structure, or like writer requirements for stats. But I think we're far from that. So I think it would be good if people could take a look at that section. It's in the change detection section, and I linked like a GitHub gist with the file level changes pseudocode and row levels changes pseudocode. I think that's it from me. I want to pause in case anyone else had any input. Yeah, Anoop.
Yeah, I think are we going to discuss the inline versus out of line metadata DV today? Or, I mean, there's some downside of keeping stuff out of line. There's some trade-off, right? It's clear to access more files to resolve the root. The other thing is, it's maybe a minor implementation related stuff, but because we moved manifest DV as a field, the representing it as an outer line Puffin based DV becomes a bit more complex, because now we need things like location and stuff like that as those subfields. You'll have a more nested structure as opposed to just having a binary field.
I think that's right. Yeah. So if we needed an out of line manifest DV, there would need to be an additional location nested somewhere for the.
I would imagine it would just be another delete manifest entry, because a root manifest can add manifest entry. So if you did want to do an out of line one, you could just write a delete manifest entry like you would inside of a delete manifest. So not in line with the reader, just as a separate entry.
Yeah, but somewhere you need to know whether this is a data manifest DV or delete manifest, right?
I
Or,
don't.
I don't
Well,
think you would. A DV is going to apply the exact same way against a data manifest or a delete manifest.
So I know I wrote this in like a long time ago, and it's led to this discussion here about whether we would want them out of line. One of my main thoughts was it should be the exact same code we're using within reading the other manifests to do an out of line. So I didn't think complexity wise it would actually make the implementation harder, because you have to be able to read out of line puffin delete manifests anyway whenever you're reading a data file. The question just is, do you want to also be able to do that in the root manifest? And I have been thinking of maybe it's not as valuable because we really shouldn't have that much in the root manifest. So maybe it's not
I
not
think
super important.
I think the other concern that was brought up is just like the IO cost of that early in the planning phase, right? So you really slow down planning. You touch a lot of things in order to just do a planning operation.
Yeah, it basically comes down to you have to go, rather than reading one file and then being able to go read your manifests, you also have to do a hash map lookup to potentially find all of the manifest DVs, and then go out and actually open those things in addition. So like it's not that bad, but it is like a bunch of extra IOs. I think these questions kind of seem secondary to me, to say, like, I think the question we need to answer is, do we need external DBs before we think about the implications of how we represent that? Because I agree, there's a good argument for, if we have external DBs, then just using the exact same DV entry and just referencing a manifest instead of a data file probably makes sense. Like, there's a good argument for that. What I've been working on, though, is trying to estimate, what would it look like to have manifest DVs in the root file? Like, what kind of storage can we get? And, what does it actually look like to determine, when would we want to actually have external DVs? So I can actually go into that if that makes sense. But I think that question, like, do we need external DVs, is the one to focus on before we get to representation.
Yeah, I think that sounds good to me. I think if we can, I guess, go into the numbers behind kind of like if it makes sense to just keep things in line versus if there's even a need for out of line DVs, manifest DVs.
Yeah, I mean, I have no strong reason to think we would need them. Although my next question then would be, are we going to write in the spec that you are not allowed to write a manifest delete vector entry into the root manifest that refers to anything in that root manifest?
So I would say strictly no, because it would be perfectly valid to have a data file. Like, for small tables using DVs, you might have only the root metadata file that contains all data files and all DVs in the root, right? So I think the question, I think the question you're actually asking is, would we disallow having a DV entry that references a manifest in the root? And I think the answer is probably yes, if we go with only inline DVs, because then we would say, for a manifest, for a metadata file, the DV is attached to its entry.
Okay. I mean, I think that's valid. I mean, then we just say that the principle here is that you should be able to process the entire root manifest without an external IO operation. So any entries that require you to have another operation before you can do anything else are wrong.
Is that confusing from the latest structure that we have? Because I don't think that the inline DB is necessarily scoped to what would only be available in a metadata or a manifest entry. So just in terms of the structure of what we put in there, like it, you know, if we say, hey, arbitrarily you can have this inline DB thing versus like, hey, this only exists in context of a manifest entry, that makes it a little bit more explicit. I'm not sure it really matters. We can always spec it, but
I think we're kind of, sorry for my background noise. We're kind of getting to where we're getting back into how do we represent stuff, but I think we want to know, what are we representing first?
Right.
well, I think we were talking about like, what are we representing, and what, like we were saying, do we want to disallow this, and is that purely just a specification based thing, or do we structurally make it just impossible to do it wrong?
I don't know if we can make it structurally impossible, because you can write content entries there. It's based on what the target of the delete file entry is, right? Like if the target is a file, it is, wait, are we saying we aren't allowing delete file entries at all in the root manifest?
No, I don't think that we could do that, because we would have delete file entries. But what I think we can do is have structs with required fields and say, like, hey, if you have a manifest content type, then you will have a manifest stats and like a manifest specific info, and that contains potentially contains this inline DB. So we can limit it through like required fields and groupings.
So what I was saying is, what if I write a delete file entry that points to a manifest file? It doesn't point to a data file. It says referenced file is now. So like that, you only know by inspecting the contents of the delete file entry.
Oh, I see what you're saying now.
That's what I'm saying. Are we making that illegal? And if so, I don't know how we can do that structurally.
So we could have a content type that is, you know, data deletion vector. And like that would make it pretty clear that you can't use a data deletion vector against a metadata file.
So we would change. We basically wouldn't have delete file entries anymore in the root. You'd have to do these data deletion elements.
I think we could still have them in the root, but it would be a different type, right? So it'd be a very specific data DB type. Yeah.
That's what I'm saying. Like it has to. It's not the old thing. It's not the old entries that we were reading before.
It would probably be identical to the old thing, but we would say like this code now means this.
Yeah, that's what I'm trying to get across.
Metadata DBs, right? Or potentially, we don't have to. We think we're introducing metadata DBs, and in which case we would say, you know, the old way of storing everything is actually referencing a data DB, not a metadata DB.
Okay,
So
I think that's fair.
To allow out-of-line metadata DBs, I mean, I think the downside is pretty clear, right? There's read latency increase. Is there any benefit? Maybe at one phase, like, you know, root becomes smaller, but again, you know, if you have to read, it's effectively an extension of the root. It's almost as if the root's bigger. Right?
With the additional IO, but yeah.
I mean, theoretically, I haven't run numbers on any of this, but like you can imagine that you want to keep the size of the root manifest very small. You have lots of files being entry, and you very rarely do deletes. And if you very rarely do deletes, maybe only like 1 or 2 entries has a delete vector. You don't want to bloat the size by adding those in, because you don't want to read those files that often. Like maybe this is a tail, and only the very oldest ones start getting these. And I don't know. I'm sure there's reasons where if you had that, you could just split them off into another manifest or something.
So I actually, you know, I think that if you think about this on the right path, if you have external DVs and you need to update one, right, you're, no matter what, reading the old DV and performing some IO operation to put a new DV file, right? Maybe you can coalesce those, but then that just means that you're scattering them all over the place, right? Because every write, even if you only write one Puffin file with the new metadata DVs every write, that's going to, over time, mean that all of your metadata DVs are in different files. So that's, you know, read time, more IOs. But if you're looking at there's going to be more IOs at write time, then I think you're probably better off in a lot of cases just rewriting manifest itself, right? Because then you're not going and needing to remove things from the manifest. You're not getting a partial manifest where you only have, say, half of the entries are still valid or things like that. So I think if you're going to undertake the cost, there are a few situations in which you want to have the IO cost, but not just go rewrite a 8 megabyte manifest.
And that also has the net benefit of like you're always improving the layout, right? So the next thing doesn't have to do that other IO, and so it like has somewhat of a compounding positive effect over time.
Yeah, to be clear, like that's exactly why I think it's worth rewriting those manifests, because you can take more things from the root and go rewrite the manifest. And so you're decreasing the root size every time you rewrite a leaf. And you know that is a big net positive for readers. So I would say like anytime, the way I think about this is like, if you run out of root space because of DV entries, you should probably make sure that you're removing the DV and also making your table metadata better in general. So that's why I think we're probably good with just inline DVs. But I also have numbers on what those inline DVs look like if we want to go through that. And this is sort of like modeling how large do we think a table is going to be, therefore how many manifest files are required, and things like, given a certain amount of load in that DV, what is the size of the DV once you compress it with other DVs? So I can go through that. That might help frame the conversation a little bit as well.
Sure.
But hold on, before we move on, I guess like one thing that was kind of mentioned there, but we may want to like take as more of like something that we should consider always is, as we're doing these IOs, and we've typically been using a number like 4 megabytes or 8 megabytes is kind of like, hey, that's the equivalent of any IO. Like that's how much work you can do in a unit. But in any case where you're doing an IO and you have a choice of producing new metadata or improving the existing metadata, we might want to lean towards saying, as a general policy, you want to lean towards improving the existing metadata. So if I'm like deconflicting DVs, like I can read 2 DVs and write a new DV, or I can read those 2 DVs and rewrite the manifest. So there are a number of these situations where we can constantly improve the metadata, and that will keep the metadata from degrading and then having to do much larger operations over time. And you're doing roughly equivalent order of magnitude of IOs and data volume.
Cool. I mean, that sounds really good to me. We maybe should write a section into the doc, just like these are decision points where you should start considering folding things into new files rather than continuing to add to delete factors.
It is principles on maintaining metadata, right? It's like,
and I think that we're going to honestly like need to look at this as it plays out. But I think given like the amount of space that we can allocate to these DVs in the root file, and completely avoid more IO operations, I think that it's compelling to say we definitely want inline DVs, because at small levels we can do a lot with metadata DVs to avoid churn in the metadata. And then as you bump up against like, okay, now my metadata DBs are too large, I don't see a ton of benefit to going and saying, okay, I've got a lot of deleted entries across all of my manifests, but the right thing to do is spend my IO operation externalizing DVs rather than cleaning up manifests. Because at that point you have a large number of deletes and you should just clean up your manifests. I'm going to relocate so I don't have the noise in the background. Excuse me for a second.
Just, we don't hear the noise. We just have the audio cut out.
I think it's probably the noise cancellation kicking in.
I do want to say sorry to everyone if I'm saying things that we've talked about like over the past 14 weeks when I've been gone. Really sorry about that. I tried to keep up. Oh, and Amok, did you want us to do review on those GISTs, the GISTs you post for change detection?
That would be awesome. Yeah, if you get a chance, that'd be good to take a pass. So yeah, one additional thing I added, it was also like trying to make equality deletes work in that logic. So that's like a little bit tricky. Well, I mean, we can't do upsert. Like we have to treat it as new rows. So that's for any updated rows. But that's, I think, it's either that or don't support them. So in the change detection.
You guys hear me?
Not supporting them. Hey.
All right.
Just so you know, we don't hear the noise when like stuff happens. Your audio just cuts out though. So it's like you stop speaking when a loud noise happens.
Okay. Well, hopefully this is better. I might have to clean up this. This is my kids' playroom, so, but it's the only room that's not very adjacent to the noise. All right. Should I share this bitmap stuff? All right. So this is how I sort of started, and this gets like more and more complicated as we go over to the right. But basically, in order to figure out how do we model some of the bitmap possibilities, I started by saying, what is the number of files in the table? So how many files are we tracking in general? And then sort of, how large are each of those files? Just to give us an idea of, what size of table are we talking about if we're talking about managing 10,000 or 5 million files. So, if we go to 256 or something like that, then, we've got a pretty reasonable, data size here. So we're talking at least 2 terabytes. And, we might be even talking about, a petabyte or 2 once you get to like 10 million files. So these are, significantly large tables. We have, once you get up here, we're getting into the quarter of an exabyte territory. So, you may not need that, or you may find that if you want the quarter of an exabyte territory, you go to larger file sizes and you can easily scale up that way. So anyway, the question to start off with is how large is each manifest? And so I've got another setting here that says, what is our target leaf manifest size? Currently we use like 8 megabytes. So that gives us, either more space or less space. I think 8 or 16 is a pretty reasonable size. So let's go with 256 and 8 megabytes here. Now, if you go and look at this, the leaf manifest size here given the number of data files and our, assumptions about how large these entries are in Parquet. And we have a pretty conservative, I think, 300 bytes for both a data file entry and a manifest entry. That gives us the number of data manifests required to store this number of data files. Now, crucially, that also gives us a pretty interesting feature that the number of entries in those manifests is bounded. So like, even though we have a billion data files in this case, we're still talking about having, tens of thousands of entries in these in the manifests themselves, which is why I actually came back here and said, let's go with 16 megabytes, because, anything under basically 65,000 or 64K is really, really small. In fact, it's one block in a roaring bitmap. So it's just kind of odd to have a roaring bitmap that is so small. Half of all of this, even at a 16 megabyte size, would likely fit in a single block in a roaring bitmap, and the other would take up like half of a block. So that's where we get the 16 megabyte size here. So that gives
the manifest entry count is the number of data files in a manifest file, right? So that's why it's going to cap at 50K, because the leaf manifest size is 16 MB-ish. Is that correct?
Yes, the leaf manifest size is 16 MBs. And this is kind of modeling, assume like we put all of the data files in a leaf manifest. Right. So if all the data files were in leaf manifests, how many leaf manifests would we need? And that kind of what we're building up to as we go to the right in this spreadsheet is, the actual size for different areas of the root file. So like, how many data manifests do we need to store? How many delete manifests do we need to store? How many data file entries, delete file entries can be, directly in there? And assuming that we are inlining things, what are the sizes of those metadata DBs?
Yeah. I think it's reasonable, but I think, as a model, but I guess this assumes that the leaf sizes are always fixed and capped at this. And as a table kind of grows, the root becomes larger and larger, right? I mean, that seems like the assumption here.
So I don't think it's unreasonable to say that the root grows larger and larger. Let me just scroll over here to the actual, root information. We're basically under 4 megabytes up through 50 million data files.
But what I'm trying to say is, like, on a very large table, it's possible that, we might want to get larger leaf sizes, so that we can have a smaller root, as opposed to having fixed leaf sizes. And
yes, yeah. So all of this is very tunable, right? What we're talking, and that's, I think, the reason why we've circled around this term of like adaptive metadata. So yes, a lot of these dimensions could just be doubled, right? If you want to double the data in your table, you could easily just make your 256 megabyte files 512 or 1024, and things like that. So a lot of this, like, you can get scale, the scale that we're actually talking about in terms of number of rows and actual data size, right? There are lots of dimensions that you can increase. Dan?
The other thing I would mention is it doesn't need to be homogeneous, right? You could actually, through procedures like we do with compaction and other things, you could make older data much bigger. Like, you can make those leaf nodes for the oldest data way larger, because they may have fewer DVs, and you may be able to reduce the overall root size by just taking slow moving data or data that isn't accessed frequently. Yeah, obviously that's more complicated, but it is entirely possible with this model. I think this modeling exercise is basically hey, everything is homogeneous. We're trying to look at kind of the worst case. If there's no maintenance, no intelligence, how is this just going to look? So it probably only gets better from here.
Oh yeah, it definitely only gets better from here, because what I'm doing here is the parts of the spreadsheet I skipped over are, data manifests and their size, and then a manifest DV load factor on basically every single data manifest. So clearly, like, you're probably not going to have a manifest DV on every single data manifest. You're going to say, oh, you know what? Take all the data manifests that don't change and rewrite those, so I'm not keeping the DV content in the root. So there are assumptions baked in here. And then we're doing the same thing for delete manifests. So how many delete manifests do we have? I'm actually saying 100% of data manifests have a delete manifest. And then I'm saying a delete manifest has actually a 20% load instead of a 5% load. And the ones that have metadata DVs are 80%. So these are like very conservative numbers in order to get to the place where we have, right, 50 million data files in a 4 megabyte chunk, even with DVs inlined. So I think that that is a good sign that once you get to 100 million, 500 million, 1 billion data files, you're generally going to want to take that principle that we talked about earlier, which is go rewrite your manifests themselves at the point where you have a lot of DV content in the root, because you're basically how many. I would have to calculate this out, but if you're saying that basically every data file has a delete or a DV against it, like we're modeling here, and there's a whole bunch of deletes against data files, and there's a whole bunch of deletes against DV files, like, again, you're going to want to take a lot of the stuff that is not changing and get rid of that, so you don't even have 4 megabytes in the root.
And just calling out that, like, basically everything up to between the 500 or 50 million and 100 million files falls within that one IO cost, right? So if we're saying roughly 4 to 8 megabytes for an IO, it's effectively the same all the way up to that scale.
Yeah, and also, like, keep in mind this number, the actual size of the table, is affected mostly by this data file size. So we're talking about a 12 petabyte table with 50 million files. And if I want to make that a 50 petabyte table, I just increase this to 1024. Right? So, like, that can increase the actual table scale without any additional metadata cost. So, like, you have to think about how you would balance a lot of the factors here. So I also want to go into a little bit of how I got to this metadata DV size, but Talat, you go first.
I just want to ask for my understanding. This is for data. We assume that data files are big, but what happens for the streaming insert cases? Like, if I have 1 megabyte files. And
so 1 megabyte files, right? Imagine turning this down to 1 megabyte, right? So your total table size, if you have 50 million files, gets much, much smaller. But I think at the same time, most people would need to compact those data files in order to get good query performance anyway. Right? If you have files at or under 1 megabyte, you have the small files problem in your read path. So, your table metadata is probably not the bottleneck that you should care about in that case. And I think we would all recommend having a compaction process that merges those data files to get back up to, large chunks of data that you can scan through efficiently in tasks.
I see. Adaptive metadata will not help to that small file problems in this case, because most probably if I have a 1 megabyte files, I need to look at the line 18 because it will be streaming insert, right? There will be so many
Yeah.
data files.
But also keep in mind, like if we're talking, 50 million, and this is with inline DVs, if you have a streaming case, right? So if you have a streaming use case and you're writing 1 megabyte files, are you using DVs? Right? Do you have DV churn in your table? Because when you run a merge statement that is producing those DVs, you're generally like, why would you not just rewrite everything and use that as an opportunity to compact? So we're already getting a little outside of a reasonable use case by imagining a table that has only 1 megabyte files, but also has all these metadata DVs. But even if we said, sure, you have the model's output for metadata DVs and all of that, and you're at 50 million files, you're still talking about a nearly 50 terabyte table with 1 megabyte files. And like, that's pretty big for a table with 50 million 1 megabyte files. I mean, I think
it's one-day streaming data, maybe.
Yeah, so
for most of the
a
time.
lot of this is like, would you use the same? I mean, my end conclusion from this is like, this helps us think about how metadata DVs scale and how large they can get, how much space in the root that we might have. But really, when you're talking about getting to 100 million or 500 million data files, you would manage this a whole lot differently, right? You would want to keep track of, hey, what parts of the table are churning and what do I have metadata DVs for? Because again, like, in order to drop size from the root very quickly, you just merge your metadata DVs back into the original files, right? And I don't think what would help is taking all of this metadata DV content and saying, oh, we're going to externalize that, so now we have to run IO operations in order to use it. Does that make sense?
Yeah, definitely. Thank you.
All right, no problem. Okay, so let's go a little bit. I'm going to set this back to 256. Let's go back and look at how I got to this metadata DV size, just so that everyone knows. And then we can also talk about representation, because we've got some interesting stuff there. So I'm going to share a different spreadsheet. Now, can you guys see that okay?
Yep.
Okay. So this is basically tests that we ran. And thank you to Amog for writing the original benchmark with different bitmap formats and different load factors. So a load, percentage load is like 1% of bits in the range set. So the range that I used for all of these tests is 0 to 50,000. And that is based on the previous spreadsheet where we said, a 16 megabyte manifest is likely only going to have about 55,000 entries. So we said, okay, let's take 50,000, and that is our space of bitmaps to represent, deletions in any metadata file. So now we're just going to say, okay, assume all all manifests are 50,000 entries. So that's about 16 megabytes worth of content, and, have different deletion rates within those. So 1% would mean 1% of the data files have been deleted. 10% would mean 10% have been deleted. And then for a given bitmap representation, how large is that bitmap? Now, how large is that bitmap is actually a little more complicated, because we're talking about storing these bitmaps in Parquet. So it is not just the size of the bitmaps added up. It is how many bitmaps can we fit in a page, and then what happens when you run Z-standard compression over that page. So what and also a big factor here is how are the bits set, because long runs of ones or zeros compresses really well. So what this does is it takes a random set of bits between 0 and 50,000. And so your compression is actually based on the number of bits set. And as we would expect, we see a peak here at 50%. So if you're setting half of the bits at random, that is going to be the hardest thing to compress. If you get past 50%, you have runs of ones randomly. And if you're under 50%, you have runs of zeros, and those things compress better than the absolute random stuff. Okay, so again, what I've done here is created a whole bunch of bitmaps, concatenated them like they would be in a Parquet binary page with a length, and then the bitmap, length, bitmap, etc. And then compress that whole thing using Z-standard to come up with the average bitmap size, which is this column here. And I think that that is a good representation of, for a given, representation in of the bitmap, how large we would actually, the bitmaps would actually be in the worst case where you're deleting random data files. Any questions at this point? Yeah, Prashant.
Yeah, I was imagining that this will be a bell curve on this one, but the line 12 of this 3,403 is a dip on the normal bell curve for this.
Oh, good point. So pay attention to this instead. So I can explain that, and that's actually why there are 3 sets of data here instead of 2. But yes, what you expect is sort of more of a bell curve or a parabola describing these rates. It's not exactly, because we don't have, until you get to 10%, we're not actually, changing the x-axis equally. But that's exactly what we see. It sort of peaks around 50%. It is mirrored at 60 and 40%, and also at 70 and 30%. And I should mention that I did the verification by actually going back and checking that all of the bit positions, once I deserialized this representation, are actually set. So we're not actually losing data and misrepresenting things.
So here, you get compression with more bits set because it compresses better. You have mostly ones there. It seems like it. I assume the dip that Prashant mentioned is because roaring switches from the dense to the sparse.
Yeah, let's talk about representation later. I just want to make sure everyone understands the actual data that we're presenting here and how it was put together. But yeah, that's why these are bolded. There's a discontinuity here that Prashant noticed. Okay, so we have 2 initial data sets. One is the roaring bitmap representation, and the other is just a Java bit set. So this is take however many bytes you need, so 50,000 divided by 8, set bits at the position that you're deleting, and write that into a file and compress it, right? As expected, you get a pretty good curve for those numbers. And just like Prashant, you noticed, and Anoop, you were trying to, you were jumping ahead to explain, we have this weird discontinuity here. So I actually have a graph of this, and it looks about how you would want it. So ignore the yellow for right now. The red is the raw bitmap, and it has a fairly nice curve, compressed. Roaring is the blue, and you can see it goes and has this really bad sort of twice the cost discontinuity here at 5%. And unfortunately, 5% is a number of bit positions set that we actually care about. Because if you're, wasting more than 5%, or, you're going to have a lot of things that are less than 5%, we assume, in these data sets. So That's not ideal. That would lead us to say, sorry, I should explain the discontinuity. Like Anoop was saying, the discontinuity here happens when roaring bitmap changes from its sparse representation, which uses 2 bytes per value for everything within the first block of 64K values. So it's basically, this is 2 times the number of bits set for everything, and you get really bad generic compression on it. When it switches to a bitmap representation for that block, it is just 64,000 bits, and it's slightly larger than the raw bitmap because it's the raw bitmap is actually shorter, because the raw bitmap has room for 50,000 bits, and roaring always stores 8K once you go to the dense representation. So it's you know, the actual like bitmap compresses a lot better than the position list. So you might think, hey, we should just use a raw bitmap, which brings us to uncompressed size in memory. Uncompressed size in memory is why you use roaring, because you can easily check positions that are set. And for a few, again, roaring is blue. For a few positions set, you get this nice property that you have a very small set of values. On the other hand, with a raw bitmap, as soon as you read that into memory, you need space for the entire bitmap itself. So that is not great. So in order to balance it, I think the question is, how do we balance these concerns, right? Is there a way to have a space-efficient representation in memory and to get that compression? It's probably worth addressing whether we care about space efficient in memory. I suspect that we do care about space efficiency in memory, especially if we have a bunch of these small bitmaps, because it can be so much larger to have the bitmap in memory, right? You're basically paying the cost of storing the full bitmap. But we would need to make sure that we actually do care about that, because the solution, I think, is adding a lot of complexity. All right, so let me go into roughly the solution that I found to produce this yellow curve. So better than roaring in memory, and better than roaring in actual on disk, or slightly better. And what I did there was I stole the idea behind roaring and used it on a 2-byte basis instead of a 4-byte basis. So basically what roaring does is it says, okay, I'm going to store 2-byte bit positions until I have 4,096 positions. And at that point, you have enough that you can just store a dense bitmap for all 64,000 potential positions in the data set, right? So if you were to store 4,097 positions of a 65K bitmap, you would be wasting space because you can just store the bitmap itself. Does that make sense? Okay, so what I did was if you look at this discontinuity, we know that we're only going to have a small bitmap that starts at 0. So a lot of what roaring does is, you know, it can have very, very large bitmaps, you know, up into the millions or billions of positions, low billions of positions, right? And it can store those very space efficiently. But we know, because these are deletion vectors, that everything starts at position 0. And position 0 is equally likely to be set as position, 65,000. And we also know that our number of the upper bound is going to be limited by the number of entries in a given data file. So the cardinality of data files in a given manifest, for example. And we know that is limited by the amount of space that we're actually willing to use for a leaf manifest. So we're wasting a lot by having, basically a block system that we're not going to use. And that block system is using blocks that are so large that you get this discontinuity. So the idea is take it down to 1 byte. So store 1 byte positions until you get 32 value. So basically say we're going to have each block is 32 bytes. Just like each block is 4,096 bytes, or sorry, 4,096 potential values. In the one that I built, which I'm calling Mumbling, I guess, we have 32 position blocks, and those are either storing a position between 0 and 255 within the block, or storing all 255 values as a dense bitmap. So basically trying to smooth out this curve by having a whole bunch of blocks rather than one single really large block with 2 very different representations. And I can go into more detail there if you guys care. But basically what we get is this curve where because we're storing it that way, we're under what would be used by Roaring, still over raw bitmap, because you can have individual blocks that fill up and get to a dense representation, taking all 32 bytes. But it's not taking all 4,096 bytes all the time. So it allows you to use some sparse and some dense positions. So you get basically a good curve on compressed size, and you get a pretty good curve on the uncompressed size. I think that the main drawback to this is the complexity of actually storing these bitmaps. It would mean Iceberg is saying we have our own bitmap representation for small bitmaps that are, say, under 1 million positions.
So
But uncompressed. Correct.
I say I have my gut first question here is, do we care about uncompressed sizes if we could just read them into Roaring bitmaps and not keep the whole bit set in memory? Because as we go through our file, we can convert them at that time, right? At a trade-off for compute. What does that look like?
So I think what is going to happen is you get one of these pages that was 1 megabyte uncompressed, and you uncompress the entire thing and take a megabyte, and then you need to you can't just use that representation. You have to allocate the space to produce all the Roaring bitmaps. And the Roaring bitmaps, yeah, they're not terrible, but they're not great either, right here on the uncompressed side. So you're basically paying both of these penalties.
So my bigger concern, though, is that if we do cleverness in terms of reducing the memory size, you have to repeat that in all the implementations. Otherwise, you get one clever solution and a whole bunch that aren't clever. At least if you specify it, you have a consistent representation and behavior.
But you can have
Trade-off.
a
I'm not saying that, because
When would it not be specified?
so
If we did it on read.
Yeah, if we used the normal bitmap, right?
Mhm.
The optimization for memory is unspecified. Like we can
Oh, yeah.
one in Java. There's I can think of a number of different ways that we can optimize the memory, but then you have to do it differently in Rust, differently in Go, differently in Python, and any vendor implementation will have to do its own optimizations as well. So it's not Like we aren't building in the memory thing. The memory thing comes from clever implementations.
Plus, like some of these bitmaps you might not even use. I don't.
So the other trade-off is practically as we're operating on this, do you ever need to actually have it in memory more than one at a time? Because you're always evaluating that against a manifest, and you're typically doing that piecewise. So
I think yes, because what you're going to do is you're going to read you're going to read the entire root file, right? And if you read the entire root file, then you're loading everything into memory. You don't necessarily know when you do that what pieces, like if you're caching, then you're keeping everything.
no, you're loading in compressed though, and then as you operate on it, you decompress, you evaluate, and so I'm just saying, like, hey, that.
I mean, I think that would support the idea of storing storing raw bitmaps and then reading into roaring, because then you would be producing your roaring representation. But I think you're still holding all of these bitmaps in memory at once, most likely. And because you're going to, I think you would do what we do today, which is like when we read a manifest list, we read the whole thing into memory and just keep it. That way we don't have to read it again at write time. And I think that makes more sense. Like use the memory to avoid an additional IO cost when you're trying to commit to the table. So we would, if you're changing any part of the table, you would still need that information. So I think it is a good argument to say, like, it gets a whole lot simpler if we just use roaring.
I want to think about this a little bit more, because we need to read this whenever we rewrite the root manifest, no matter what. On scans, we always have to read this as well. We have to read file names and this, all other stats and other things we can potentially ignore. So those are like the two cases where the in-memory size matters of this, because it dominates in both of those cases. Well, it won't dominate in the full rewrite because we could potentially have column metrics, but not even something we care about. But for reading, for every scan needs to read this whole thing.
And okay, so this brings us back to the first spreadsheet that we were talking about, right? So I basically took a regression model and used it to predict, given some bit load, how large MDVs were going to be. And then as we go out with all of our assumptions here in the green boxes, you get to where, again, we're talking about up to 50 million data files in under 4 megabytes. And really that size is dominated, like very much dominated by the DVs themselves.
Yeah.
Right. And so do we have random positions set? Do we really carry DVs across the entire table space? Right. Like the pessimistic assumptions here are really adding up, and we're still getting to 50 million data files. So I think that where I came to was, this shows that inline DVs are definitely valuable to avoid having additional IOs, right? At the 1 or 5 million data file tables that are still quite large themselves, right? Like you're well under a megabyte, even with all of the DVs that you're storing. And so the cost of not worrying about that IO is great, right? And if we're saying that, this is really the cost of your cache, then again, like, I don't think we really care about that cost of, caching the root metadata for a table at these table sizes. It gets different once you start talking about 100 million files, but also at 100 million files, like if you're talking about having so much churn that you are still having these expectations of like 20% load on your metadata DVs and 80% of your DV manifests have metadata DVs, then like that's pretty crazy in itself. And I think getting back to our initial question, would you rather externalize the DVs, store them in a whole bunch of random Puffin files, or would you rather start rewriting metadata files and manifests? I think it's pretty clearly you would rather, start rewriting manifests here.
You've got me sold on that. I'm sold on inline here. Now I'm thinking more about this in-memory representation. I'm trying to think about from a planning perspective, and also I think the current manifest entry size is kind of low. I'm thinking that we practically may see them being more balanced in how much space they're taking, and like what is the uncompressed size of the other elements that you need to read for planning. Because I know people have been talking about adding in other things like Bloom filters or other junk, which might make this even smaller in comparison and maybe not even worth optimizing on.
I would be very surprised if Bloom filter. Well, sorry, I agree with you that like this might not be worth worrying about. This is the compressed size that we're showing here, though, and so the question is, if we're talking about remember our 5% load before was pretty atrociously large on disk.
Are we talking about like 50,000 bytes uncompressed? Like there's 50,000 entries in the.
So keep in mind that this is currently 8 for us in Iceberg.
Okay.
So that means we're actually, well under our 50,000 here, which makes everything smaller. But at the point where you're getting to some of these bit set sizes, like you're talking like 2K per.
Yeah, I'm just saying the worst case uncompressed is still 25K here, or 28K, whatever our manifest entry count is. That's like the biggest the bit set can be here.
Yes, exactly. And if you take that 28K, then look at this discontinuity, 4096 divided by 28K is, quite a large. So basically everything is going to be in this section, assuming that you're not, loading above like 20%. So is that okay? I mean, that seems a little crazy to me. But then, yeah.
That's what the uncompressed size of the other things we're going to try to load at the same time are.
Yeah. So
that's where I'm worried, because like if we're going to try to load something else that ends up being like 100K, then making this from 25K to 4K or 3K feels less important. But
it's the number of bit positions that are set. And, once you get a lot of bit positions set, you start hitting this in memory size as well, because, it doesn't even take down the total size. If you have a space of values up to 27K, you're still like, once you hit more than 4096, you're going to blow it out, and you're spending 8K per bitmap no matter what. So I suspect that better data in terms of actual write patterns, actual loads, and actual sizes on these metadata DVs, it will almost certainly be smaller than what we see here. I would almost lean towards saying like just going with roaring makes everything simpler, because then we don't need implementations of a specific bitmap type. You get a decent, like, this area hurts, but it's not that bad in terms of size on disk. But again, the main problem is our size on disk is inflating that cost of the root metadata. So if we really care about the root metadata size, and we're going to have a lot of these, then we should go with, I think, the other clever approach rather than just a raw bitmap. Something to think about, because I think we're 10 minutes over.
Yeah.
Sorry about that.
Sorry, I'm thinking about it a lot. I'm just like, I'm trying to think about it in terms of how many additional columns would this be? If I had added like another 20 columns to my table, is that equivalent to me making this benefit? So like, if we're dealing with people who have 200 columns in the table, is this really that much of a difference?
So that's hard to say, because additional columns in the table you can ignore in Parquet. And like,
Other than our root size, though, if we're trying to do things based on that.
what do you mean?
If we're trying to keep our root
oh.
manifest to a particular size on disk.
Okay, so additional columns in the table is going to drive up the entry size because you're going to have more stats. It's going to drive down the number of data files in a given manifest. And therefore, once you account for that, you're going to have smaller bitmaps in general.
Yeah.
Right, so you're going to be more in this area with higher percentage rates.
But we're not collecting stats for, most columns, right? There'll be a cap, I assume.
Our
And
default
maybe-
is 200.
Maybe what we do then is, we base the number of files rather than on size, just base it on number of entries. I mean, that if we're doing the inline DVs like this, maybe that's a better tuning parameter than manifest size.
I actually was supposed to have left too. Thanks for bringing this up. This is really interesting. I'm going to think about it some more. If we're voting or anything, I'm on board with no external Puffin files.
Great. I that's the conclusion I came to as well. All right, thank you guys. We'll circle back the next time, I think.
Thanks, Ryan. Thanks everyone.
Bye.
Bye.
Bye-bye.